Hello, 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 hello. Testing. Okay, let's start. Anyone understand this meme? What do you understand? Several different things. So why we got this meme? Anyone know? You know who is this cardinal? Bishop in the Catholic Church, the priest in the Catholic Church. So last week they picked their leader called Pope in the Catholic Church in Vatican, and that Pope has a bachelor in mathematics. So he's a mathematician. Yeah. So if people ask you what you can do with your bachelor in maths, you can be a doctor. Yeah. Okay. Quite versatile this degree. You can literally do anything you like. Okay. So next up, we will introduce Hausdorff space. Hopefully today we will cover everything you need for your assignment. Last assignment before your midterm. Okay, let's motivate this concept here. So in Rn, we say that each each 1-point set is closed. Why is it closed? Hey, where's Ivan today? Where's the closed guy? So why is it closed? You need to check that the complement is open. Okay. Or there's another observation here. Okay, there's another observation here. So we will say that actually it might be because for any point x not equals to x naught, there actually exists an open neighborhood of x that avoiding snake. Okay. Actually, you can observe this also. Okay. Okay. Well, so from here, you could show that actually the closure of the 1-point set is just itself. Okay. Or you can use the use the intersection of all the closed set containing S naught. Okay. In particular, S naught is a closed set that contains S naught. But actually, this is not true. The singleton set being closed is not true in general. Okay. In general, it's not true. In particular, for a very simple example that we have seen before. Sorry? Say again? This huh? This is a set bar. A bar equals to A. Yeah. A bar equals to A. The closure of singleton set is a singleton set. But this is not true in general. Okay, so for example, we just look at the 3-point set topology we had. For example, let's pick this one. Okay, by now you should be able to show that this is a topology. Okay, so can you find a singleton set that's not closed in this topology here? What's the singleton set that's not closed here? There's 3 choices only, A, B, C. Choose one. Larry. B is not closed. Why? Okay, because AC, so X take away B, because AC is not open. Okay, if you want it to be open, you should include this guy in, right? Okay. 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 So let's continue. So we'll introduce conversion first. Let's introduce conversion first. Should we do conversion? Hey, hello. Okay, so let's do conversion here. So definition. In a topological space, okay, we'll define conversion now. A sequence x1, x2 points of the space X converges. Okay, converges. So in MA, right, when you do convergence, right, you will talk about epsilon delta or epsilon n. Epsilon n. So for an epsilon, you want to find an n such that for every greater n, your point will stay epsilon close to your limit point. Okay, but here we're going to define using open neighborhood. Okay, so a sequence converges to point x in X if for every open neighborhood U of X, okay, there exists an n in N such that Xn live in the neighborhood for all little n greater than Bn here. So what's the difference between epsilon n and this open neighborhood definition? What do you think? No distance. Okay, so in particular, we replace epsilon with open neighborhood. Okay, we replace epsilon with open neighborhood. Okay, so another thing is if we define this sequence here, so just now is first motivation. Let's look at the second motivation here. So in Rn, right, you will prove that if the limit exists, it will be unique. Okay, but with the same topology we had just now, but let's say the 3-point set topology that we considered just now, A, B, and C. Okay, we claim that there's no unique limit for the constant sequence B. Okay, why? Why there's no unique limit for B? So where B converge? Where B converge? Okay, so you need to show, you need to take the point, right, and test whether it converge. So if you want to say that it converge to B, maybe you will guess it's B because it's constant. Then what you need to do, you need to check that every open neighborhood of X, you will contain B inside the neighborhood always. Okay, for all the terms in the tail in your sequence. Okay, so how many open neighborhood that contain B? I hung with how many open neighborhood that contain B? Sorry, two, two. Which two? A, B, good. B, C. How about this circle? This circle is also open. This what this circle means? Hanwei. What does this circle means here? Huh? The middle one. Can you see or not? Singleton, good. Okay, so this is a singleton that contain AB, and then you have AB, and then you have BC. There's one more, right? Actually, two more, huh? The entire set, empty set, good. So actually, there are 5 of them to check. Okay, so there are 5 open set here. So it's but open neighborhood of X means what? Open neighborhood of X means what? There are 5 open set here, right? So open neighborhood contain X means what? What is the definition of open neighborhood? Sorry? So there's a, so okay, so let me put here. So you should have a open set O such that O contain X, but O is inside U. I don't know. Okay. So 5 of these, right? I think only 4 of them qualify. Right? Because empty set, there's nothing there. So inside this 4 open set, right? Is B inside there or not? You need to check that there exists an N such that Sn is in U. But what N works? What's the N that works? What's the big N that works? Yeah. If you want to say that B is inside all these open set. Sorry? Sorry? You can answer over. I'm asking everyone. You can answer. You want to answer? No? I'm asking you now. So what N works? Or n, good. Okay, you just pick n equal to 1 or to work. Okay. So this shows that B is a okay, so this shows that Sn converge to B. Okay. You can ask another question, does Sn converge to A or not? What do you need to do? You need to check all the neighborhood that of X. Sorry, of A. Okay. So what are the open neighborhood of A? Obviously A, B, and then A, B, C, two of them already. But these two open set got B or not? So the term from your sequence or not? Then what n will work? Also ON. Then this says what? A is also a, or we haven't defined limit point yet. So as this constant sequence will converge to A also. See it? What are the open neighborhood that contains BC and also ABC? But BC and ABC both will contain B also, always. So actually this constant function are converged to 3 points. The limit is not unique. Okay. Okay. So these observation actually lead us to define Hausdorff space. The following definition. Okay, so definition. Topological space X is called a Hausdorff space if for every distinct 2 point in X, there exists a open neighborhood U1 containing X1 and U2 containing X2 such that their intersection is empty. Okay, so first thing we will establish is as in our motivation 1 is actually every finite point set in a Hausdorff space is closed. Okay. Yeah. Up. Yeah. Okay. Okay, so it suffices to show that every 1 point set is closed. Okay, because you can use a finite union of a closed set to show that finite union of 1 point set is closed. Finite point set is closed. Okay, so let's just focus on showing a singleton set is closed. For the finite point set case will follow from the finite union of closed set. Okay. So how do we do? What do we do here? Well, you see, there's not very much assumption you can use here. Okay, in particular, there's a big word here, Hausdorff. Okay, so let's use it. So for any point that's distinct from S0 here, okay, what can we do by Hausdorffness here? There exists open neighborhood U containing X1, or use X, just X, and U V containing X0 such that U intercept V is empty. Still remember what's the equivalent property that we deduce for a point being living inside a closure? X in A bar means what? Anyone can recall what we have proved last week? Okay, S in A bar, if and only if every set U containing X intercept A. Okay, so the contrapositive is what? If you found an open set that containing X does not intercept A, then X is not in A bar. Okay, as long as you can find one open set that contains X but doesn't intercept H, it will not live in A bar. Okay, so just now, what do we have here? For any point not equal to S naught, you found an open neighborhood such that this open neighborhood intercept the open neighborhood containing X is empty. Okay, so since U does not intercept X naught, the point X doesn't live in the closure of S naught. Okay, so the only thing that live inside S naught is just S naught itself. Sorry, the only thing that live in the closure of S naught is S naught itself. Which says that the singleton of X naught is okay. Okay. Any question? So far, okay. Okay. A bar equals to A implies that A is closed. We recall this. What's the close? So this is a metric space close. Okay, you should look for the topology close. Topology close. 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 We have A bar equals to A, then A is closed thing. Let's delete this. Sorry. 哪里？上面这个 where is it at? Let me find. But this one is one direction, right? If A is closed, then A equals to A bar. We want to use that A equals to A bar, then A is closed. A equals, see, why A equals to A bar implies A is closed. Here I put definition in. By definition, A is closed if and only if A equals to A bar. Hey, no, this one is we haven't reached here yet. Have we defined close using S bar? We haven't met this definition yet. If A equals to A bar, why A is closer? We define. Let me think. So intersection. Okay, so maybe we can make a lemma here. So intersection of a closed set, when is it closer? Finite intersection or arbitrary? Arbitrary intersection closed set is closed or finite only? Arbitrary. Okay. So by definition, A bar is closed. Okay. Yeah. So by definition, A bar should be closed. Okay. So maybe I make a proposition here. So in A, okay. So we'll say that in A is open and A bar is closed. Okay, so we got two directions now. Okay. By the property on topology, arbitrary union of open set is open, arbitrary intersection of closed set is closed. And then you have the other direction also. Okay, so that we have if and only if. Okay. Okay. Let's continue. So this will lead us to make a definition of topological space. Satisfies a T1 axiom here. T1 axiom if all its finite point set are closed. Okay, if all finite point set are closed, then we have the topological space to satisfy T1 axiom here. Okay, so let's make a remark here. Hausdorff space, we have proven that it implies T1 axiom. Okay, but not the other way around. Okay? If you just had a finite point set to be closed, it's not enough to build Hausdorff space. Okay, so you might think that a Hausdorff space is something about open set. Okay, and then T1 is about point set to be closed. Okay, so for example, let's give an example to this the inclusion here, no, implication. So for example, the real line R with the finite complement topology. Okay, finite complement topology means what? A set is open if the complement is finite. Okay, finite set topology here is not Hausdorff. Okay, although you know that the real line with Euclidean topology is Hausdorff, but if I change the topology, then it's not Hausdorff. Okay. Yeah. Okay, but we still have a 1 point set to be close. Well, so maybe we don't show it here, but one thing you can try to do is the hint you can try to do is actually this finite complement topology, right, is generated by these bases here. Okay, U alpha. So there's a 2U here. So people complaining this 2U is too close. So I put a U alpha here with U alpha. 两个杆这样子。Okay, how about I use O alpha then? Okay, so what's this open set here? This open set is a bunch of union. Okay, union from negative infinity to n1, union n1 to n2, union blah blah blah. union up to NK2. Okay. Okay. Make sense or not? This open set here. Does it make sense? What's the complement of this open set? Complement is what? N1, the Ni's, right? But this Ni only finitely many. Finite complement topology. Okay? Because the complement is finite. So these things are open. Okay? Make sense? Okay. Because I mean, how to think about this union set here? You should think of your real line, right? Okay, but you want a set that its complement is finite. Okay, so you should take all these open interval. Cannot. Complement of these open interval is finite point looks like this, right? Okay, so you don't want the you want the middle. Okay. Makes sense or not? Right? The complement of your set is just finite. So these are the Ni's, N1, N2, N3, and so on. Okay. Does it make sense? No question or not? Feel free to ask. I won't score you stupid one, never mind. Okay. 什么？我会骂你啊！会讲你笨。嗯，因为我也是笨，不用紧，大家一起笨。Yes. Sorry. What do you mean? No. Wait. So this is just a basis element for your finite topology. Finite complement topology. Yeah. So my point is, use this open set to help you see these Hausdorff space and T1 property. These help you to build the open set because when you talk about Hausdorff space, what do you need? Open neighborhood, right? Okay. When you talk about T1, you also can use open neighborhood to talk about it just now, right? Okay, so you need a description of your open set. So now I'm giving you a description of open set. Okay. Okay. Well, do you want to think a bit on this Hausdorff space? If you take 2 points here, what do you need to do? You need to find 2 open set that avoid each other. Is it clear that you know how to do it? Huh? So, well, okay, let me try. So let's take XY here. So you want to find 2 open neighborhood that contain X and Y, but their intersection is empty. Huh? Midpoint is midpoint like this, S plus Y over 2. And then? So let's make open set around X first. What is it? Huh? X minus X plus Y over 2. Huh? Okay, and then X plus Y over 2. Oh. Uh-huh. You mean like this? Is this the complement of this set finite or not? No. So it's not an open set in here. Any other idea? Negative infinity from where? From here. Here, this part. The complement of this set, Still infinite now, because on the other side, you can go for it. Why not put all the way up to y? Union y to infinity. The complement is just y. Open up. How about let's pick another open set for y then? Huh? Can we do this? We pick a open interval for x. For y, I mean. Do the same. So let's try. I take if I take up to x. Okay. What do we need to check for Hausdorff? The intersection is empty, but this two intersection kind of not empty, right? So what to do here? Why? What do you mean why? Huh? So you think this is Hausdorff or not Hausdorff? Not Hausdorff. Huh? So not Hausdorff, what do you need to prove? There is this 2 point such that for every open neighborhood that contain so you need to show for every okay. So for every open neighborhood that contain x1 and x2, they are non-empty, the intersection. Okay, not not empty, right? Not Hausdorff. Okay, so not empty. There's this become for every. And then there's this 2 point. There's this 2 point distant point in X such that for every open neighborhood, their intersection is not empty. Okay, I think there's some argument you need to do here because you need to show for every. But now I found one open neighborhood for you to show you that the intersection is not empty. But what can you see here? The actual intersection actually is quite large. Quite large. So no matter how you pick your finite, no matter how you pick your open set in your finite complement topology, right? You can see that the intersection actually is infinite. Because finite means what? You only can throw away finitely many points from your open set. Okay, I think you should use the density stuff to show that the intersection is always not there. Okay, yeah, you could try and write it up. Dawson, can you write it out? Try and write this argument up in your Excel. 让赵生写，让赵生自己写。OK，OK 啊，可以吗？赵生，可以写吗？可以，我相信你。OK，all right. Similarly, you can try and show this is not this is T1. Okay. Next theorem. Suppose your topological space just satisfies the T1 axiom. Okay, and we have a subset X. Then we say that the point X is a limit point of A. Have we defined limit point of A last time? We did, right? Because we need to do A bar stuff. So how do we define it? Every open neighborhood. Excuse me. So if a point is a limit point of A, meaning what? Every open neighborhood around X contain a member in A other than X itself. Need to be other or not? Other member in A or just a member in A, isn't it? Huh? So other member in A, other than X itself. You think so? So let's check. What's the limit point definition? Where do we define limit point? So now we are slowly putting all the ideas together. So make sure you know these concept well. Okay, so here is a metric space limit point. So you need to move to a topological limit point. Okay, yes. Okay, so we also use open neighborhood to define limit point here. And we will say that every open neighborhood of X intersect A in some point other than X. You can try and modify this definition. If you just require it to intersect X, you include X into this. What happened to this definition? If you don't require other X, other point than X. Okay. Then you will somehow include the case of isolated point into this limit point. Okay. Yeah. So this other than X itself is pretty important. Okay. If you throw away other than X itself, then you consider X inside A, then you might include the case of isolated. Okay, so we will deduce that this is true if and only if every open neighborhood of X contain infinitely many. Okay, so you can also see that this is a very familiar proposition we have proved for metric space. Okay, can recall or not? So let me recall then. Just now I think I passed by it. This is D, right? You see, in metric space, what do we do? Every open ball center an X. Okay, so in topological space, we change this open ball become open neighborhood. Okay, so last time we also proved that in the metric space, usually we put D for metric space. We also show that if X is a limit point of A, then every open ball center an X contain infinite of points from A. Okay. So similarly, you have this theorem in the topological space. But in this topological space, right, we don't even need to be Hausdorff, or we just need it to be T1. Okay, we just need it to be finite point set to be closed. We already have this limit point property. Okay, so more fundamental property on the Euclidean topology is it is T1, not just Hausdorff. Okay, so a finite set being closed already give you this limit point property here. Okay, you don't even need to know Hausdorff. Okay, just T1 is enough. Okay, this proof is similar to what we had before. So let's skip this proof. But we'll do one interesting one. Theorem. If X is Hausdorff, then a sequence of points of X converges to at most 1 point in X. Okay, so we're gonna prove this. This is not an epsilon delta proof. This is an open set proof. Okay, so let's prove this one. All right, so you want to show that converge to a unique point, right? So a very standard thing to do is suppose it converges to two different things. Converge to two different things. But your condition is just being Hausdorff. Okay, so try to use Hausdorff's then. So by Hausdorff property, there's this open U in X and V in Y such that U intercept V is empty. Okay, but by the convergence of Xn to S, right? What does it mean? Convergence. For every open neighborhood, there's this N. Okay, for every open neighborhood. So in particular, there exists an N such that Sn will be living inside U. Okay, for all n greater than or equals to n. Okay, because U is an open neighborhood. And Sn converge to X. Okay, but we know that U intercept V is empty. Okay. And then this Sn all the capital N. Okay, let me make we draw this picture then. So let's say we have a U here and then V here. U, V, U. Okay. So maybe your Sn jump. And then after a great N here, Sn here, Sn plus 1, Sn plus 2, all of them live inside U already. Okay. Meaning what? Meaning V is an open set that cannot contain Sn for n greater than or equals to n. Okay. So for n large, right? All your Sn live inside U already, but you know that U and V, the intersection is empty. So, but Y is inside V. So you cannot get your tail, of sequence really close to Y. Okay, so this means what? Hence, Sn cannot converge to Y. Okay, does it make sense? Okay. Yeah. Is it much cleaner than epsilon delta, epsilon n? Okay. Yeah. Okay. Okay. Before we're taking a break, let's make the final definition here. So if the sequence Xn converges X in a Hausdorff space X, so we'll define what you usually see in MA. We will write Xn converge to X. Okay. And we say that X is the limit of the sequence Sn. Okay. So it's only makes sense to define limit inside Hausdorff space. Okay. Like what I showed you just now, can converge. Okay. In different space, you can converge. but maybe you converge to different point. Then we won't call those limit, too many limit. But here we got a unique point to say. Okay, so we call this a limit. Right, so meaning what? In your first year, second year, those limit right as this unique is because it is a Hausdorff space. It's Hausdorff. Okay, if it's not Hausdorff, then maybe you converge to different thing, which is not unique. Okay, any questions so far? Any questions so far? 小童呢？很久没有看到他，不知道。Okay, let's break until 11:03.
对，你觉得就很烂，没有啊，一定是并不是真的那个系列拍的最烂的，但我觉得演的还是的，因为我们看有些看以前原漫画。That's the Marvel's show。有很久以前，7年。基本上是。Daredevil 这个小说。也没有啊。就是他就是那种超人的脸。我还是比较喜欢这个。我没看，我看过一部很古早的。哦，我也看了他那个。我知道，那我别了。没必要生气，对吧？没有，就是其实还是从看着他有哪怕节奏高过。
他们做的太好了。
对。网飞的夜魔侠基本上能把这个感觉都塑造的很。然后你想，才能跟女性的。哎呀，我跟着一个人选择。不要高一点。感觉这个还是不喜欢一个。什么意思？现在专门投入是研究上的一个。哦，以前我那个表上
早上不是我看到有一个情侣，像你们这样就抱着走，我以为是你，就这样抱着然后走的，我以为是你们，然后看着抱，然后就是一个抱着一个，然后再走着，哦，你每次会做的事情。好玩吗？是啊，我是没有我在看是不是你们，然后看哎什么？我觉得我想包这种飞，这样，脚同步的时候很爽。哦 ，OK， 很搞笑。
那个我要办考试了，他一点我听，所以我要想。因为你的声音对吧？然後第二咧，我試嚟嘅食啲即係咁樣做，跟住呢啲已經後面就成日同埋我嘅啲嘅，因為我旁邊睇過，我嗰陣時當針起來，我直接跟那種很好的旁邊先把器材把它關掉，然後就是往更好一點的站起來。也可以。也不是还没提二零，但是我只要去那种，你看个带那个，那发现中国人都是哎，全人家来骂我，他们哎是真好吗？生怎么没发给我干？哇，然后非常太低，看不清，要。不行，那是啊，地方就是在我们，这我还是打光枪那个，然后我在那边都没有这个，呀，可以在 IG 和。我觉得没有必要，就是我觉得没没有这个一模奥运需要的东西，让那个但是这些都是搞不太懂的，挺好。因为通常那个那有意思我。然后我去了，生命。我那个都没搞，他只是哦，我也做过这个。这个我大部分我也不是在炒肉，因为要调整。那个就是把这个违法行，
你们等一下要看 epsilon delta continuity 跟 open continuity 是 equivalent 的 proof。
你那时候我们没有已经看过，
看过啊，会啊。
你干嘛笑？哦。我还没都给他。遇到我那个时候，我在网，在铁军拿过，那200打我，把200就拿到，送200。好，刚开始玩的时候，抖音上，对我这张给我，对，有时候有时候在我们带有点出不好，我给他们。
Hello, testing. Okay, let's continue. Okay, before that, tonight we have a revision class. Have revision class for your midterm Friday. We will discuss assignments. I already returned your assignment 3 already. Assignment 4 is still marking. So I release a solution also. Yes, midterm next week. Yes, Friday 2 to 4. Okay. Friday 2 to 4. Okay. Please prepare. You can bring in A4 double-sided handwritten notes. Okay. You can bring your definition, anything in. Okay. Make sure you bring definition in. Sorry. Yeah. A4 double-sided. 什么? Yeah. Okay. So please bring definition in. Otherwise, if you copy a lot of question, I didn't put out the question, then you will not benefit too much. So please put definition in. You can put examples also. Some technique, proof of technique also you can put it in. Okay. But please don't put any sticky notes on your A4 paper. I got students do that. 懂什么是 sticky note 吗？贴那个便利贴上去。OK。Then 呢，当场没收哦，当场没收啊，不要等下在那边哭啊。Okay, one thing I want to remind you if you do anything that violate the exam, right? Okay, maybe I will confiscate it. Okay, but don't cry at the exam time. Most of them, right, didn't listen to me actually in the class, and also didn't check out the announcement. Okay, so maybe Jia Yi can help remind them before the exam also. Okay, yeah. A4 double-sided. How small you want to write doesn't matter, but it's handwritten, no printing. Okay, no printing. Okay, just handwritten, must be handwritten. Okay. Right. We will continue to next half of this chapter, which is about continuous function. Okay, continuous function. So we have done with topological spaces. I want to talk about function between them. Okay. So we'll define that. Let's take two topological spaces. Power x and power y here. We'll define the function x to y is said to be continuous. Okay, continuous if for every open subset B of y. Okay, open subset here just mean open set plus subset. That's all. Okay, nothing special here. Then the set of inverse of V is an open subset of X. Okay, so by now you should think about your epsilon delta definition, right? So this is really inspired by epsilon delta definition here. So let's say that if f is continuous, okay, let's say we talk about real value function with one variable, then for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in between. Okay, so we need to say continuous at where, right? So let's fix a point. Continuous at a point P. Okay, for all point P that is for all point that's a distant delta away from P, we will make sure that Fx minus Fp is reading epsilon 2. Okay, so you see, what we have made is we make this inequality here, strict inequality here, into an open set condition. Okay? If you have an open set in the domain, you will have an open set in the, sorry, the other way around. If you have an open set in the domain, then you will have an open set in your domain. Okay, you see, this as all epsilon has to be true in the codomain setting. Okay, then there's a there exists a delta that works in the domain setting. Okay. Can see or not? Can compare or not these two? Okay, so we have make this two part here become open condition. Okay, is it open or not? Is it an open ball here? Is this an open ball here or not? What's this open ball here? Between P minus epsilon and P plus epsilon here. This one here? Fp minus epsilon and Fp plus epsilon. This is the two open ball here. Yeah. 什么？对 P 点 delta，我刚才讲错哈。P minus, so this x here is living in P minus delta, comma P plus delta. Where the other one is Fx is in Fp minus epsilon and Fp plus epsilon. Okay. So far, okay? Okay, no? Okay. So continue. Okay, so there's a remark here. So let's make a few remarks here on how to check something is continuous or what can happen to this definition here. So the first remark is, it is actually okay that the open set you started with is not in the image of your function. Why? If it's not in the image of your function, what is the pre-image of this open set? Lydia. If it's not in your image, right? So what's the pre-image? Anything get mapped to it or not? Nothing. So meaning what? The pre-image is empty. But it's still fine, right? Because empty set is an open set. Okay, so you really can check for any open set in Y, not just the image of F. Okay, which is still open. Okay, remark 2. So the continuity really depend on few things here. Continuity really depends on F itself and the topology of the domain and codomain. Okay, it's very specific one. Because if you keep the same function but change the topology, maybe it's not continuous anymore. Okay, so this three things is very important. So F going in between X and Y here, this topology is very important. Okay, because you need to talk about open in the codomain and open in the domain. Okay? So if you fix your function but change your topology, maybe this function is not continuous anymore. Okay, very sensitive to topology. Continuity here. Okay, and remark 3 here is For example, if you want to prove that continuity with maybe the codomain topology, you know that it's generated by some basis here. It is probably enough to just check on basis. Okay, like what we did for closure. Okay, it actually suffices to check what happened on the basis element. Not need to check the general open set, because you can build your general open set using the union of these basis element. Okay, so I'll write down what it means in mathematics format. So because for every open O of Y, okay, what is O here? We can write it as a union of basis element. What this implies, if you look at the inverse of this union, right? So that's why we spend a lot of time doing set theory before. What is the inverse image of a union? Okay, actually it's equal. Okay, it's equal to the inverse image of every component. Okay. Okay. Okay, so then actually, if you want to know that the arbitrary open set is open, just need to check that every inverse image of your basis element is actually open. Okay, so similarly, you can deduce a similar idea for basis. So for topology that generated by subbasis. Okay, in subbasis case, you have intersection here, right? Finite intersection. Okay, but at the same time, you have the same equality here. If you want to apply inverse image on intersection, it's also the intersection of the inverse image. Okay, so just need to check on the subbasis element is enough. Okay, continue. So first example, I think we want to show that for continuous function, f from R to R is, so all continuous function from R to R is continuous. 感觉很白痴，很白痴啊这句话。Can anyone decode what this sentence trying to say? 此 continuous 非彼 continuous. So first continuous is continuous on what? Yeah. Okay, so actually this is a epsilon delta continuous function. We want to show that it is a open continuous function. Openness. Okay, so there are two directions to show here. So let's do it. Well, we will write down the argument, and then I will draw the picture for you later. Okay, to see what this proof is trying to do here. Okay, so if you want to do epsilon delta imply open continuity, right? So what do we do? Open continuity. What's the definition? For every open subset in your codomain, you want to show that the pre-image is open. Okay, so just take any open set V in your R. Okay, and then we want to show that F inverse V is open. Okay, like just now, right? The set, what's the possibility of a set? It could be empty. Okay, if it is empty, then you are done because empty set is open already. Okay, this could happen when the open set that we take is not in the image of F. Okay, but if not, there should be something inside there. So assume that there's something inside your F inverse V. But if there's something in X is in F inverse V, or what does it mean here? What's the definition of inverse image? How can you live inside an inverse image here? So Fx is living inside V. This is the definition of inverse image. Okay. Okay, not so far. Definition of inverse image. How to remember? One way you can remember is I apply f on both sides. Maybe this will confuse you, or you might think that f inverse is a what is that inverse function. Okay, but you just apply f on both sides. Okay, but v is open, oh. Okay, but this is open in where? This is open in Euclidean topology here. So what does it mean? V is open, oh, meaning what? There exists a epsilon. Yeah, open neighborhood, correct. So how to build open neighborhood in R using the open interval, right? Okay, so there exists a epsilon greater than 0 such that fx minus epsilon to fx plus epsilon will live inside V. Okay, there's an open ball living inside this set here. But you see, you have an epsilon already. What can you do? This means what? By the epsilon delta continuity, what does this epsilon give you? There exists a delta depend on this epsilon such that x minus delta epsilon to x plus delta epsilon, okay, will be living inside f inverse of yes.对啊，全部 epsilon 都可以啊，所以现在我要用它了啊，我要用啊，哪一个都可以啊，只要全部都可以用的话，我现在有一个 specific。Okay, does it make sense? For every there's this one, right? So in particular, I pick one epsilon, there will be careful. Every epsilon, there's a unique one that attached to this delta. This epsilon, okay? Okay, so since this is true for all x in f inverse v, it follows that f inverse v is okay. Any question or not? No, okay. Okay. I think the other direction is obvious. Okay. So let's assume the openness and then prove the epsilon delta. So you want to show for every, right? Okay, so let's take. Okay, before that, this continuity function, right? This says that it continues at every point in R. So let me go up a bit. So you see, what's the difference between these two continuity here? Okay, the first part here didn't mention any point. Okay, but the MA version one, it start with continuity at a point first. Okay, does it make sense? Okay, so there are things you need to take care here. So just now, actually, you need to prove for any arbitrary point. Okay, so if you want to prove the epsilon delta, then you need to start with a point first. And at this point is arbitrary. If it is word for arbitrary, then it's continuous at every point. Okay, So let's take x naught and take an epsilon delta, sorry, epsilon. And then we will consider an open set here, which is fx minus epsilon, comma fx not my plus epsilon. Okay. So well, this is open. Okay, this is clearly open in R. Okay, by the openness continuity, right? It automatically gives you that F inverse V is an open set. Okay, in R, in the domain R. Okay, but how do you cook out the delta from here? Okay, how do you cook out delta from here? How do you cook out delta from here? Okay, well, you obviously you should use F inverse V to be open. No? Okay, then there should exist a basis element, okay, such that this basis element contain S naught, and at the same time, this basis element should contain in F inverse V. Okay, because F inverse V is open. Okay. Then what? How do we choose delta here? We just choose the delta to be the minimum of S naught minus A or B minus S naught. Okay. Why it works? So let's see. If my X is in between delta distance with X naught, okay, the point that we make sure must live inside, must be living inside AB, which in turn live inside, which in turn in F inverse V. So Fx must live inside V. And Fx live inside V means what? The V that we set is such that Fx, the absolute value of Fx minus Fx naught is less than epsilon. Okay. Let's summarize a bit in the picture here. Let's put 2R here. Okay, so if I say that I want to be continuous at the point P, and then this is FP here. Okay, let's say we put a FP minus epsilon here, FP plus epsilon here. Then here we'll go P minus delta. Okay. So if you start with a random open set, right? If you start with random open set here, maybe this open set is not regular. Okay, it's not regular. Okay, let's talk about open continuity first. So if you start with a random open set in codomain, right? It might not be regular. It might not be regular. It might not be regular. It might not be symmetric around this point here. Does it make sense? You don't worry. If you want to consider open set contain FP, right? It might not be symmetric around here. Okay. 听我讲吗？有人听得懂我在讲吗？听不懂。So if you look at the open set around FP, right? It might not be regular. 我们知道什么叫 regular 吗？什么叫 symmetric 吗？啊？非常麻烦点儿。OK，
要 regular 我就好了。
昨天那个 regular。Okay, so okay, first of all, do you agree that this FP minus epsilon and FP plus epsilon is symmetric around FP? Agree or not? Left to right difference is the same. If I pick different open set, right, it might not be symmetric. Agree? Okay, ma. Everybody. But the point of openness continuity is if you look at the pre-image, okay, if you look at the pre-image of this this pre-image, I don't want to say this is an inverse function. It might not be regular also. Okay, but if you are continuous in the sense of epsilon delta, it works. Why? Because if it is open here, meaning what? You can find a, if it is open here, you can find a regular epsilon delta inside your open set. And then you can use your epsilon delta to pull back into a open set here, which is regular. Okay, so this is how epsilon delta continuity implies openness. But how about the other direction? You want to use openness continuity to imply epsilon delta. You start with a regular interval first, open interval. Okay. And then you look at the pre-mesh. But the openness continuity might not give you a regular interval on the domain. Might be something else. But delta one is very regular. How to find a regular interval here? Because we know that this pre-mesh is open. Open says what? There exists a open set. Okay, basis element, correct? Open set that contain P, but contain in this open set pre-mesh here. So from this basis element here, you can try and build a regular one. Does it make sense or not? So from here, you think which one is better to use? Which definition is better to use? Which definition is better to use for continuity? Epsilon delta or open? Which one? Never mind, you just pick up. Huh? Just pick up, never mind. Open, why? Not exactly. Yeah, something about that neighborhood. That neighborhood is no longer need to be symmetric at the point that you want to consider. 不用这个左右要一样的，不用，只要包含它就可以了。Does it make sense or not? For epsilon delta definition, you must make sure that you have this plus epsilon minus epsilon distance from your point. But open set doesn't care. No need to care one. As long as there's an open set contain P, that's all. Okay. Does it make sense? So maybe I cannot make a video for you. Maybe I draw it for you. Okay. 1点半, I think quite good. Okay, so here is epsilon continuity. Here is openness continuity here. Okay, let's draw a few epsilon delta and open ball. So here, let's say it's FP, FP, P, and P here. So what does epsilon delta continuity do? So you need to start with multiple epsilon. Okay, start with multiple epsilon. Right. Start with multiple epsilon. Okay. You want to find a delta. Okay, you want to find a delta like that. Very regular one. 很整齐的 epsilon delta. But openness, you can jump. Okay, maybe first open set is like this, second open set is like this, maybe third one is like this, and then fourth one is like this. Maybe next one is like this. Maybe the other one is outside also can. Then inside, if you look at the pre-image, as long as open set is fine, also can simply jump one. Okay, Ama? Does it make sense? These two turns out to be equivalent. Okay. Understand? Okay. So that's why the max I do at least is different from the some lecturer here. Because even though you want to do it strict right sometimes, but actually randomly is also can also works. Okay, actually there are more freedom here. Does it make sense? Okay, ma. Okay. Okay. So what are the others? Continuous function, maybe you can consider all those things from your calculus 2. Okay, calculus 2, curve in planes, curve in space, function of two real variables, three variables, vector field, all these are continuous function that you consider in calculus 2. Okay. So maybe right. Does it make sense or not? Okay, let me write it down. So in calculus 2, you consider R to Rn function, okay? R to R2, R to R3, for example. Okay, so these are curves in plane for R2. And then R3, we call it a space curve last time, okay? And you have a height function, right? From R2 to R, function of two variables. Three variables also have, okay? And then there are vector field also. Okay, these are all continuous function. Okay, you consider from calculus 2. And one more thing I want to break your old intuition, okay, is identity function might not be continuous. Previously, you might think that, oh, identity function always continuous, right? It might not be continuous. How do we do this? Obviously, since it is a continuous, identity function, right? So we can't really change the set. We can't really change the set, but we will consider identity function from R to R with different topology here, which is the lower limit topology. We can change topology, but we cannot change set. Okay? So this function is not continuous. Okay. This identity function is not continuous. Can anyone think why? What's the lower topology here? Can anyone recall or not? So what are the open set here for TL? These are the union of half closed open set, right? Okay, so maybe put AB here. Okay, why is it not continuous? So you need to think about your definition. What's the definition says? For every open set in the codomain that exists, the pre-image of this open set is open. So go and take an open set here. I already tell you how the open set looks like, right? So what's the pre-image, for example? What's the pre-image of open half closed interval AB? Huh? What's the pre-image of this under identity map? Seng. Yes. So what's the pre-image of this interval? 这个 map 是 identity map，没有做动，就是送去一样的地方。你要送回来，对。啊 它 close 什么？送回一样的地方，为什么？对，没有错。没事，你知道你在讲什么啊？所以就是因为它是 identity map 嘛，x 送去 x 嘛，x 的 pre-image 只有 x 哦，OK，就是，yeah，okay. But this thing is not open in the Euclidean topology. Not open. 看到？OK，哎，怎样说 not open 啊？不是说它 not close 哦，不是说它 close 哦，怎样说 not open 这个东西？How to show this is not open? There's a few way to show. 啊，中意，在比什么？啊，给它一个 interval，然后A 那边附近给它一个 interval，然后呢，为什么这个可以 imply 这个东西不 open？它会 contain 外面东西，然后呢，这代表 A 是什么点？还是 A 不是什么点？A 也可以是什么点，也可以不是什么点。OK，非常好。第一件事情你做对了，去找 A，去旁边做 open ball。But then what does this ball tell you? It intersect point outside the set. So 它告诉你这个 A 是什么点，还是不是什么点？这个 OK，它告诉你 A 是个 boundary point，因为 always intersect the set and the complement set。还有呢，A 不是一个 interior point。So meaning what? You found a point inside the set that is not an interior point, and the set is not open. Okay. Because to be open, what do you need to show? A equals interior A, 或者 A is in interior A. 每一个点 every point in A must be an interior point. Okay. Yeah. There's a lot of way to show this actually. Okay, but 更乱的一件事情是，我可以反方向。Then this set is open. This function is continuous. 反一下它变 continuous 了。So here, which is 等一下让我 let me finish the previous argument first. So which is not open in R. So sorry, here I should put identity. So identity is not continuous. But if I change the other direction, become continuous become continuous here. If you look at the identity 2 inverse of an open set, just now we said that just is enough to check on basis element, right? So basis element for Euclidean topology is just open interval. Okay, but what is the inverse here? 来，再问Seng一次。What is say? So what's the inverse image of open interval AB? 还是 identity map，一模一样的 map，一样，所以是 AB good，很好。OK， but open interval AB is actually open in the lower limit topology. Why? 为什么 Why is this open in a lower topology limit? Huh? How to build this open interval using half closed interval? How to build? Can the dama build using half closed interval? I think last time Joshua gave some construction, right? Which one? So you got a AB, right? Okay, how to build? How to build like this? Oh, 越来越近。How? Some number. What number? B over n. B minus A over n. Okay. Then take n from 1 to infinity. Okay, so you take A and then plus this difference here. I mean, well, first term, what do you get actually? Close B, take away B, right? It's empty, but it doesn't matter. You need an empty set. Okay. Then you continue your interval getting closer to A, but okay. Make sense, huh? Okay, so it's a infinite union of open set in a lower topology. Okay, which is open. Okay, so identity 2 is actually continuous. Okay, so really sensitive to topology, this definition. Okay, so maybe you will think that there's some defect in our definition here, because in epsilon delta, right, we really start from defining continuity at a point, and then we deduce a continuity at a set. But now we do the other way around. Topology is always doing the other way around, right? Last time I showed you one of the examples already. So we define continuity on the whole set first. Then now we will define a continuity at a point. Okay, so again, let's consider f x y. Okay, there are few equivalent definition here. Maybe we won't prove it. Maybe we'll just discuss it. I will put the proof inside the notes. So the following are equivalent. First, if you have a continuous, openness continuity, then what you can show is for every subset of X, actually f of A bar, okay, f of a closure, okay, live inside the closure of FA. Okay. Third is, because this is an open version of continuity, right? You can similarly define a closed version. So for every closed set B of Y, then the pre-image of B is also closed. Okay, what fourth is, so here we'll do at a point. So for every X in X, and for every open neighborhood, V fx, okay, there will exist an open neighborhood U of X such that Fu is in V. Okay, if there's a single point that satisfies this condition here, there's one X that such that for every open neighborhood here, this word, then this is a continuity. But now our continuity word for every point in X. So you need to put every point in X. Okay, so if you close this, right, this looks like the epsilon delta definition. Right, this just looks like the epsilon delta definition. Okay, what's the V inside your epsilon delta definition? This is the f of X minus epsilon s plus epsilon. But this one is more general. This is just an open neighborhood. Okay, no? Does it make sense? Okay. Okay, actually, these are equivalents. These are equivalents. What time is it? 11:47. Okay, we have 3 more minutes. So which one do you think is not obvious at all? Maybe we can talk about it. Which one is not obvious at all? What do you think? Huh? Jingsen? Two maybe it's not obvious. Why you can relate continuity to a closure? Okay. Why you can relate continuity to closure? Yeah, I agree that 2 is not obvious. Okay. So one thing you can try to prove here, right, is 1 to 2, 2 to 3, 3 to 4, and then no, 1 to 2, 2 to 3, 3 to 1, and then 1 to 4, 4 to 1. Okay, this is the proof I will present to you in the notes. Maybe we can try and see what does 1 implies 2 means. Okay, if you have continuity, openness, continuity, right? Why you have this closure inclusion here? Okay, so you think of A first. Okay, what is A bar? Last time we proved already. It's just A with the limit point. A with the limit point. Limit point means what? Every open neighborhood around this limit point, you must have point from A. Okay. Now you want to map F. Okay, map this A and a limit point across. Okay. Says what? It should live in the closure of FA. Closure of FA means what? You have A, you take F, map across first, and then you take all the limit point. So what you should imagine here is, oh, the limit point of FA seems to include the image of the limit point of it. Makes sense? You have an A. Okay, so maybe like this. Maybe draw the picture first. Okay, so let's say you got an A. Okay, you got an A, and then you map it across. Okay, become FA. Okay. So let's say your closure here of A maybe looks like this. Okay. So you F of your FA, right, should also live inside the closure of FA. Okay. Make sense? I think the interesting part here is you only have one inclusion, not equal. Okay, maybe you can come up with an example that's continuous, but these two sets is not equal. Okay, but just now, but this the one I draw to you is equal. Yeah. Right. Think about it. Let's see if we want to prove it or not. If not, I just leave it as a homework. I will put the proof to you so that you can refer. Okay, any question? Any question? I think by now you should have enough thing to finish your assignment already. Yeah. Yes. Yes. Oh, okay. Yeah, sure. Okay, then how about it? Huh? Which one is not equivalent? Sequence definition of closure. Limit point. Uh-huh. Why not? You sure?
Yeah.
But sequence sequence. Okay, let me think. Oh yeah, sure, because just now I produced a wait. So what are you asking? Uh-huh. Mm-hmm. Mm-hmm. Why then?
It's a sequence in that way. So, like the limit FX and like still within that.
Oh, let me think. Oh, so you are saying that so you are saying that if I have a sequence that converges to a bar, point in a bar, and then I apply f across, and then that f, oh yeah, sure. Yeah. So if you have a limit point in a bar, right, you have a sequence that converges to that point. Just now we also prove that it's equivalent to this open neighborhood definition, and then you apply f to it. It's a sequence in fa also. Okay, but how about f of that limit point? Okay, the point here say that f of that limit point is actually the limit of that fai. Yeah. Because in the continuity definition, what do you need to satisfy? Left-right limit is the same, and then you need to achieve that limit. You need to achieve that. Yeah, you need to achieve that. Okay. And then there are a few ways to achieve that limit, right? You can achieve from your FAI. Or you actually need to achieve from your X. Okay? Yeah. You can use that way to think about it because epsilon delta is equivalent to sequential continuity. Yeah, so in MA, right, these three definitions are equivalent. But this proof is an open set proof. Okay, this proof is an open set proof. Yeah, I just use epsilon delta or sequence to make you think about what you have learned. But this proof here is only about epsilon proof. Sorry, open set proof. Okay, open neighborhood proof. Okay, you can see that open neighborhood proof is actually quite clean. Okay, very clean, cleaner than you do the epsilon delta stuff. Also, sequence stuff. Okay. Any question? Okay, if not, see you tonight. Tonight I'll bring some snack from Ipoh for you to try. I just came back from Ipoh. Huh? What?盐焗鸡，怎样带回来？坏掉带回来。